Hello and welcome to this 7th lecture of Introduction to Artificial Intelligence and Machine Learning for Engineers. So today we are going to talk more about machine learning. So we are still talking about machine learning. We are talking specifically about supervised machine learning. So when you have some data for which you have both the feature and the label, so you have both the input and the output, and your goal is to predict the output as a function of the input. So we are going to continue to talk in this case about regression problems, where your goal is that you have some features and you want to predict what is the corresponding observation. You want to predict a given property, a property that can continuously change, and you want to predict this property based on the knowledge of the feature. And today we are going to talk about a very important problem in machine learning in general, which is the problem of underfitting and overfitting, which is something that is a very general feature of machine learning. Every time you build a model within machine learning to predict something, you will all have to worry about avoiding the issue of underfitting and avoiding the issue of overfitting. So today what we are going to talk about in this lecture is how to avoid the issue of underfitting and overfitting. We are going to see what it means and how we can avoid it in practice. So to illustrate the issue of underfitting and overfitting, so let's consider an example. So let's assume that your goal is to predict the strength of a given concrete. So this is the strength of a given concrete after 28 days. So after you mix some cement and some aggregate with some water, the concrete will develop some strength, and you measure some strength after 28 days. And here you have the measurements in megapascal. And you want to measure this as a function of how much water did you use in your concrete. So the x-axis in this case here is the ratio of water per cement, like the mass of water divided by the mass of cement, something that we typically call the W/C ratio. So in this case, this is y, this is the observation. The observation in this case is the strength of concrete, and the feature that you have and that you want to use to predict the observation is the water to cement ratio, which is going to be your variable x. So in this case, if your goal is to predict the strength of concrete as a function of how much water do you put in concrete, there is a true function. There is a perfect function that should be able to describe this. When you mix water with cement, this is a chemistry problem, and if you know exactly how much water you put and how much cement you put, then you should be able to know exactly what will be the strength of concrete. There is nothing random in that. You should get exactly a true function. So this blue line here is the true function if you were able to know perfectly what is the water, what is the cement, etc. So in most of the time when you're trying to predict something, if it's something that is governed by science, then there should be a true function behind it. Like when you have certain types of effects, certain types of causes, those causes are going to result in a given effect. And if the relationship between the cause and the effect is governed by some physical or chemical laws, then in theory you should have a function that relates the cause to the effect. For example, if you are trying to predict the acceleration of an object as a function of its mass and as a function of the force that is applied on this object, then you know that you can use the Newton's law of motion, that the mass times the acceleration of an object is equal to the sum of the force applied on this object. So in this case, there is a real mathematical function, which is that force is equal mass times acceleration. So this is what you have usually when you're trying to predict some behavior that are governed by some physical laws or some chemical laws, which is the case here with concrete. That being said, in real life, when you make a measurement of something, you always get some noise in the measurement. You always make a small error, an error that is never equal to zero. So for example, here, if you were to measure the actual strength of a concrete, first, when you actually mix some water with some cement, maybe you are going to do a small error. You cannot be entirely sure exactly how much water did you mix with cement. So that's one thing. The second thing is when you make the measurement itself, when you measure the strength of concrete, then again, you cannot get a perfect value. You will always get a small measurement error when you do this. No instrument has a perfect precision. And then there is some other things, some other source of errors. Like for example, if the temperature, the ambient temperature is changing, then you might get different results. So there are some other aspects that that can influence the measurement. And sometimes if you do 10 times the same measurement, you will get 10 times different values. So in real life, you can never measure this true function, this true blue line, which would be the true perfect relationship between the water to cement ratio and the strength of the concrete. This is something that cannot be accessed in real life because you can never make a measurement that is 100% accurate. So when you actually measure the concrete strength, what you will get is some result that hopefully are not too far from the true function, but you will never get exactly the true function. You will always get some noise. So those are going to be the actual measurement that you will get. Those are the actual observation. So when you do a measurement, you never get the true function directly. You always get an approximation of a true function. So the actual measurement that you will get is always going to be an approximation of the real function that you are trying to model. And that would be the same for everything. If you are trying to measure the acceleration of an object after subjecting this object to a given force, the real function should be that mass time acceleration equal force. But in real life, if you measure the acceleration, you will never get this true acceleration. You will always get some approximation. You will always have some noise in the data. The data in the real world is always noisy. You always have a little bit of uncertainty every time you do a measurement. So what you will get in practice is this. So here in the blue line is still the same. This is the true function. This is the true function that you are trying to model. This is the true chemical law or the true physical law. But this function, you can never access it directly. What you can get is some measurement. When you do some measurement, you always get some approximation of the true function. You never get the true function itself. There is always some noise that is associated to the measurement. And this is when you're trying to model a chemical or physical process. But when you're trying to understand something, for example, involving humans, like trying to predict human behavior, then it's even worse, because in this case, there is no true function, because there is no chemical law or no physical law that is governing the behavior of humans. So in this case, the only thing that you will get is some measurement. You can get some measurement, measure the behavior of a lot of humans. You will get a lot of data points, but there is no true function. And so when you are trying to do machine learning, your goal, what you want to find is to find this function. You want to find this blue line. If you knew this blue line already, then there is no need for machine learning. You already know how to convert x into y, how to map x into y. But in most of the time, we don't know this real function. Sometimes this real function exists. That's the case for physical laws and chemical laws. The only reason that we don't know this blue function is because our knowledge of the chemical process or the physical process that we are trying to understand is just not good enough yet. But there is an underlying law that is governing this process. And in some other cases, like when you're trying to predict human behavior, there is just no law. There is no real function that we can think of. And what you want in this case is to build a model for something for which you have only a certain number of data points. So again, this true function here, we know that sometimes it exists, but in practice, it's always invisible. If we knew this function, then there would be no need for machine learning. What we want is to find a way based on measurement to try to infer what is this true function. We want to, based on some examples, some actual measurements, for example, measurements of concrete strength in this case, how can we use machine learning to go back to this true function, or to at least find a function that is a very good approximation to this true function. If we have a model that can give this true function, then it means that in the future we will be able to predict the strength of any concrete for any amount of water. We will be able to have a model that we can use to make some predictions. So just like we talked in the last lecture, this is a regression problem. You want to find how to map x into y. That being said, what we talked so far, we have talked about linear regression, and we found we saw last time that by applying the conjugate gradient optimization method, we can find the best linear function that can map the feature x into the observation y. Here, the problem is that if we use the algorithm that we saw last time, which is linear regression, what the linear regression will find is that it will try to find the best linear function that is giving a relationship between the input and the output. So maybe it's going to look like this, but clearly in this case, a linear model, a linear hypothesis is not a good approximation of the data. It's clearly too simple. When we look, even if we don't know the true function, when we look at the data point, like the orange data point, we clearly see that those data points is showing a maximum and then is decreasing. So we know that the function should be like this. The true function, we know that it should not be a linear function. It should be a non-linear function that has a maximum and then will start to decrease at a high value of x. So in this case, we cannot use linear regression because in the case of linear regression, we necessarily assume that the hypothesis, that the model is a linear model where y is going to be a linear function of x. So in this case, we need to move to a non-linear model. That being said, there is nothing very complicated about that. The only thing that you have to do is to create some new features. So that's something that is always going to be a key step in a machine learning model, is that you need to think about what are the features that you are going to use as input for the model. In the case of a linear model, what we have used is just the feature x. But if you want to move to a non-linear model, we can still use the same algorithm. We can still use linear regression. We can still use the conjugate gradient to find the best model. But all we have to do is to add some new features. And so what kind of features can we have in this case? Rather than having only x, what we can have is having x2, x3, etc. And we can add various degree coefficients, various powers of x. Why? Because in this case, if we add some new features, rather than having only x, if we have x2, x3, x4, etc., then it means that now we will be able to model a more complex function, which is not going to be just a linear function, but potentially a parabolic function, a quadratic function if we add x2 as a possible input. It can be a cubic function if we add some a term x3, and more generally, like if we have a lot of different powers of x, then the model that we will be using can become a complex polynomial with a degree n. So now it means that now we will have much more flexibility. We have more degrees of freedom to fit the function y as a function of x. Why? Because now in the case of the linear model, all we could say is that the hypothesis is that our prediction of y, we can write it as just a linear function. So this is the model that we use for the linear model. Now we can do exactly the same thing, but now say that rather than having only x, we will add some new features. So now we will say that the new hypothesis is going to depend not only on x, but also on x2, on x3, etc. And we can go up to any power that we want. And now this hypothesis, rather than writing it only as a linear function, we can write it in terms of first an intercept, theta naught, plus theta 1 times x, plus theta 2 times x2, etc., plus theta n times x to the power n. So now if we write the hypothesis like this, then it means that now we will be able to fit more complex functions that are not just linear function, but can be quadratic, cubic, etc. So it can be a complex polynomial of degree n. That being said, the algorithm is going to remain exactly the same as the one we saw. We are still going to use something that is exactly the same as linear regression, and we are going to use the conjugate gradient optimization algorithm in order to find the optimal values for theta 0, theta 1, theta 2, etc. So just to see that it's exactly the same thing. So like in the case of the linear regression model that we just said. So in the example that we saw in the previous lecture, we said that in this case, the hypothesis is that you have a model that is going to map x to y, which is the property that you are trying to predict. And in this case, if you are assuming a linear relationship, so the model is that the observation is going to be predicted as being a linear function of x, so theta naught plus theta 1 times x. So this is when you have only one feature. This is a linear model when you have only one feature that is x. That being said, if you have now another feature, like for example a feature x prime, where you have two features now, not just one feature but two features. For example, if you're trying to predict the acceleration of a given object as a function of the mass of this object and as a function of the force that is applied to this object, then you will need two features. You need to know the mass, you need to know the force. So now you have two variables, and in this case, if you wanted to do this, you can do exactly the same thing, but rather than having one feature, you have two features, but it's still going to be a linear model. In this case, you can write that the hypothesis is now going to be a function of two features, not just x, but now x and x prime, where x prime is the second feature. So now your model will depend on two inputs. It's still a linear model, so you can express it as an intercept plus a coefficient theta 1 times x plus a coefficient theta 2 times x prime. And that would be exactly the same thing. That would be a linear model, but now you have two dimensions instead of just one. You have two features, two inputs for your model. Now what we have is a more complex model where we said that we are going to write our hypothesis as with the following input, with x, x2, x3, etc. up to a given power n. And in this case, the model can be expressed as theta naught plus theta 1x plus theta 2 x2, etc., plus theta n xn. So here now it's a nonlinear function because there is some quadratic term. So now it's a function that does not linearly depend on the feature x, but can have a quadratic dependence, a cubic dependence, etc. That being said, it's exactly the same as a linear function in the context of linear regression. Why? Because you can, if you want to define a new variable, you can define a variable ui, which is equal to x to the power I. So if you define this new variable ui, which is equal to x to the power y, you just introduce a new variable, you just change the name. Now if you rewrite your hypothesis, now your hypothesis is going to depend on not just x, x2, x3, but now it's going to depend on u1. u1 is the same as x to the power 1, so it's the same as x. On u2, on u3, etc., up to u to up to u index n. So now it depends on n variables. Each of those variables is x to the x to a different power. But now if you just rewrite this function, you can rewrite it as theta naught plus theta 1 times the first function, the first variable, plus theta 2 times the second variable, etc., plus theta n times the nth variable. And you see that here it's exactly the same as a linear model. You have, in this case, you have n features. Those features in this case turn out to be x, x to the power 2, x to the power 3, x to the power 4, etc. But nevertheless, in the context of linear regression, you can still treat them as n distinct features that you can rewrite as u1, u2, etc. So those are n features, and in this case you can just apply exactly the same algorithm. You can apply linear regression, but rather than doing it in only one dimension with only as a function of x, now you will do it in n dimension with n different features, which means that now you will have a model that can depend on n different features. And if those features you take them as being a different power of x, then it means that now you have the ability to fit a function y as a nonlinear model that can be a complex polynomial of x up to a given degree n. So now when you have more than just one feature, so we can call this multivariate linear regression. So again, it's still a linear regression. There is nothing different. You're still doing a linear regression, but if those multiple variables turn out to be x, x2, x3, which is your choice, you can define any variable that you want, then usually we would also call this polynomial regression, just because in this case the different features have different polynomial degree of x. So in this case, when you have more than just one feature, it is usually more convenient to think of the feature in terms of vectors rather than real numbers. So one thing that you can do when you do this is, rather than having the different features being x, x2, x3, x4, xn, etc., it's more convenient to define a vector of all the features. So typically what we will do is to define a vector, which is the feature vector, the vector of all the features. And in this case, what we will do is to define a vector where each of the component of this vector is going to be the different features. So you will have x, x2, x3, etc. up to xn. So you are going to define your vector like this. And usually what we will do is to add the first component of this vector to be 1. So we will see why we do this, but just think that this first element of the vector, so it's the same as x to the power 0. X to the 0 is the same as 1. And we need to add this factor 1 because this is the one that is going to be related to the intercept of the model. So we are going to see in a few seconds why it's needed. And then since your model now is going to be expressed in terms of theta naught plus theta 1 x1 plus theta 2 x2 etc. up to theta n xn, now we can define another vector, which is the vector of the coefficient of the model. So we can do exactly the same as what we did for the features. We can define a vector that is going to contain the different coefficient of the model. So theta 0, theta 1, theta 2, theta 3, etc. up to theta n. And you see the reason that we used a term 1 here is so that the two vectors here have the same size. In this case, those vectors have n plus 1 elements. So they have the n features x1, x2, x3, x to the power n, etc., plus an additional feature which is just the related to the intercept. So here, each of those two elements have n plus 1 elements. And now if we do this, if we write this feature like this, we can rewrite more conveniently the hypothesis of the model. Why? Because first we can define we can take the transpose of this vector. So if we take the transpose of the coefficient vector, now it means that instead of being a column vector, it will become a line vector. So what we can rewrite this as just as a line. So the theta naught, theta 1, theta 2, theta 3, etc. So when you take the transpose of a matrix, you just invert the line and the column like this. And now what we can do is we can rewrite the hypothesis of the model as being h. It depends on the feature x. The feature x, the vector x, is the input of the model. And now, rather than having this model being expressed as a complex sum like this, we can just express it as a product of matrix. We can express it as the product of the vector transpose of t times x, where this is a matrix products. So as a reminder, when you do a product between two matrices, for example, in this case, you are doing the product between this you are doing the product between the transpose of theta. So in this case, the transpose of theta is theta naught, theta 1, theta 2, etc. up to theta n. Then you are doing a product of this with the vector x, which has first component is 1, x, x2, etc. up to xn. And as a reminder, when you are doing a product between two matrices, what you will do is the product of this element times this element plus the product of this element times this element, etc. So it's going to give you 1 times theta naught, which is theta naught, plus x times theta 1, which is theta 1 plus times x, plus theta 2 times x2, etc., plus up to theta n times xn. So this product between the two matrices here is exactly the same as what we wrote this, but expressing the features as a vector and the coefficient as a vector make it possible to have a much more concise way of writing the hypothesis of the model just as a product of two vectors. And this is going to be pretty important because in most of the real-world machine learning models, you have more than one feature. You have potentially a high number of features. So in this case, it's always more useful and more convenient to express them as vectors. And when you are going to implement those machine learning models in MATLAB or in Python or in anything else, it's going to also be more convenient to write those features as different vectors because it's going to make the calculation much faster to calculate some operation on vectors rather than doing some loop on all the features. So in this case, expressing all the calculation as vectors and calculating some product of matrices, etc., this is going to really speed up the calculation quite a lot. So now the question is, if we are going to use this algorithm and by defining new features, x, x2, x3, etc., the question is, how many of those features should we choose? What is the maximum degree that we should choose? And that's going to be a very important thing in machine learning, is to find what is the right degree of complexity for the model. And having a model that is not complex enough is going to be an issue, and having a parameter that is a model that is too complex is also going to be an issue. So for example here, if I take this function, the question is, should I fit it with just a degree 1? So if I just fit it as a linear model, maybe the model that I will find will look like something like this, which in this case would be too simple. It doesn't really capture the trend of the data. So another option would be to fit it with a degree 2 to fit it as a quadratic function. If you fit it as a quadratic function, then maybe the function that you will find will look like something like this. But in this case, again, it's a quadratic function doesn't look like to be able to capture the trend of those data. So then you can say maybe you are going to fit it with a degree 3. Maybe the degree 3 is going to do something like this, which maybe is going to be a better choice, but maybe you could get even better choice by fitting it with a degree 4 that maybe, I don't know, will look like something like this. So the question is, where do you stop? And in this case, is it just good enough to take a very high maximum degree so that you can fit very complex function, or is this going to be an issue? So to illustrate the problem related to the complexity of the model, let's try to see what we would get in practice if we were trying to fit those data with different degree. Let's see what we would get. So this is what you would get if you just were using a degree 0. A degree 0 means that you assume that your model in this case is just theta naught with no dependence on x. Then in this case you just assume that your model is just a constant number. So clearly that would be too simple, because that would not capture any relationship between the input x and the output y. So now this is what you would get if you use a degree 1. So by using what we saw last time, which is just a linear regression where your model is a linear function of x. So in this case, if you do this, so as a reminder, the blue function is the true function, which is the function that you don't know, but that's the function that you want to guess. You want to guess what is this function that is relating x to y. You don't know this function, but ideally you want your model to be as close as possible to this function. You want your yellow model here to be as close as possible to the true function blue, but you don't know what this true function is. So in this case, as you can see, the yellow line is not doing a bad job, but it's clearly not capturing the complexity of the model. It's making a big mistake here. Like the error is going to be pretty high. Like it's not good at capturing the complex relationship between x and y. So now this is what you would get if you use a degree 2. So if you assume a quadratic relationship where your model now would be a quadratic dependence on x as theta naught plus theta 1x plus theta 2 x2. So as you can see here, again, it's a little bit better than the degree 1. Now you're capturing the non-linear relationship between x and y. So you are capturing the fact that x will, when you're trying to look at y as a function of x, now you're capturing the fact that there is a maximum here, that y is a function of x that shows a maximum. And so clearly it's better, but it's nevertheless not very good, because so you are making a pretty big error here. You have an error here, like this part is not so good, and here also clearly the function starts to diverge from the true function. So that being said, it looks like a pretty reasonable choice to fit this function, but it's not perfect. So now let's move to a degree 3. So now you are fitting your function as a cubic polynomial. So your model will be theta naught plus theta 1x plus theta 2x2 plus theta 3x3. So now you can see the function is pretty good. It's not quite the same as the true function in blue. Like your model is not exactly the same as the true function, but it's pretty good. It captures almost all the features of the blue function. So now this is what you would get if you were to do now a fit by including 4 features. You do a degree 4 where you include x, x2, x3, and x4. And if you look carefully, you see that your function yellow is really doing a good job at properly going through all the points of the list of the features that you have, the list of the observation that you have here, like all those measurements that you have. Your function is really doing a good job at going through all those points. So the only reason here that we know that this function actually doesn't necessarily look as good as the model with degree 3 is because in this case I showed you the blue function, which is the true function. Here we see that when we use a degree 4, the model looks good when we compare it to the data point that are measured, because it's really going through the middle of all the data points. But when we compare it to the true function, then it's actually not as good as the degree 3. But if you don't know this true function, which in practice you will never know this true function, then it's very easy to think that this degree 4 is actually better than the degree 3 model. So now this is what you would get if you use a degree 10. So now that you have a degree 10 function, it really has a lot of freedom. So as you can see, now the function is doing a lot of effort to really go through all the points that you are using to as an input for machine learning. So as you can see here, like the function is varying a lot so that it can go through almost every single point of the data set that you are using. So here, as you can see, the function, if you just compare it to the data that you are using to train your machine learning model, it looks like this function is doing a very good job. But when you are actually comparing this function to the true blue function, the true function that we don't know, then we can see that the function starts to be really oscillating a lot. It starts to deviate quite a bit from the true function, the blue function that we are trying to model. And now, as a last example, this is what you would get if you really go to a very complex model with degree 20. Now you can see that the function is almost perfectly going through every single point of your data set. Like your function is oscillating a lot so that it can really go through every single point. Like the function is doing an excellent job at interpolating all the points that you are using to train your machine learning model. But as you can see here, like it has nothing to do with the real function anymore. It has nothing to do with the blue function that you are trying to find here. So here, this example is to show you that when you try to model, when you try to find a function, here the only thing that you know are the data. The only thing that you know are the orange data, and based on those data you are trying to infer this blue true function, but you don't know this function. You are trying to find this function. So here what you can see is that if your model is too simple, then you will not be able to have a good representation of the true function. Like you will not be able to really benefit from the data that you have, and you will underestimate the complexity of the data, and your machine learning model will be too simple and will not be offering a good approximation of the true relationship. It's not going to be a good approximation of this blue function. On the other hand, if you are using a very complex model, then the function that you are going to be developing as your machine learning model will really go through every single point of your examples, of your observations. But then in this case, again, it will not be a good approximation of the true blue function. So in this case, you would be doing a pretty bad job, because now if you are if your model, your machine learning model looks like this, you cannot use it in practice to predict anything, because now if you want to use this model and to predict the strength of a given for a given amount of water, you will use this model and it's going to predict some very crazy thing. Like it's going to predict that for some amount of water the strength will be very high, for some others it will be very low. So you will not be able to use this model in practice. So the complexity in machine learning is when you don't know this blue function, which again, you'd never know this blue function in practice. Otherwise, that would be very easy to determine which one of those degrees is the best. But in real life, all you know is the data, the measurement, and based on those data, you want to find what is the right degree that gives you the most realistic model. So that's the main, one of the main difficulty in machine learning is to find the right level of complexity for your model. It cannot be too simple, but it cannot be too complex either. So now that's the main difficulty, is when you have some noisy data like this, and this is what you have, this is the data set that you have, and your goal is to find the relationship between x and y. You want to be able to predict y as a function of x, and you don't know what is the true function behind this. That's what you want to find. Then the question is, in this case, would you use a degree 1 model, or would you use a degree 3 model, or would you use a degree 10 model? And it's very hard to decide to make this choice, because if you just look at the degree 1, maybe it's obvious to see that it's not doing a very good job. But if you look at the degree 3 or the degree 10 looks actually even better than degree 3 if you don't know the true function. Like the degree 10 looks like it's really interpolating very well each of the data points that you are using to train your model, like each of those training data that you are using here, each of those measured observation that you are using to train your model. The degree 10 model looks like it's really doing an excellent job at capturing all those data. So in this case, the question is, if you don't know that this degree 10 does not seem to really offer a good approximation of the true function, is how do you decide in this case what is the best degree? So one possible idea would be to look at the accuracy of the model. So as a reminder, one way to look at the accuracy of the model is to calculate the mean square error. So the mean square error, as a reminder, is going to be the sum of over all the observation. So you have m observation in this case. You do the sum over all the observation. You take the difference between what your model is predicting for the observation I, and you take the difference between the true value of this observation I, and then you take the square of this sum, so that you cannot have some positive difference that will counterbalance some negative difference, and you calculate the mean of this by dividing by the number of observation. Another quantity that we sometimes look at, which is almost the same as the mean square error, the MSE, is the Rms C, where R stands for the root mean square. So the Rms C is just the square root of the MSE. So if you want to calculate the Rms C, all you have to do is just take the square root of everything here, and you get the Rms C, which the main advantage of the MSC, the main advantage of the RMSC as with respect to the MSC is that the RMSC will have the same unit as the observation that you are trying to fit. For example, here you are trying to look at to predict some strength. You're trying to predict the strength of concrete, which has a unit of megapascal. So if the strength, if the unit of the strength, that is to say the unit of Y, is in megapascal, then it means that when you take the square difference between the predicted strength and the true strength, then the unit of the MSC is going to be in Pascal to the square. So it's a little bit hard to understand sometimes the meaning of this RMSC. Like it's if the MSC is very large, then it means that you are making a large error. When the MSC is very low, you are making a small error, which is good. But if I'm giving you a value in square megapascal, it's hard to know if it's a high error or a low error. But if you take the square root of the MSC, so now if you calculate the RMSC, now the unit of this, since you calculate the square root, will be in megapascal. So the value of the RMSC is a little bit more intuitive because it tells you in megapascal what is the error of your prediction. So it's something that is easier to understand, a number that is easier to understand, because you can compare it. You can compare this error in megapascal to the average strength of a concrete to decide if it's an error that is low or high. So if you calculate the RMSC of those different models, this is what you would get. So here on this plot, what we have is on the y-axis, this is the RMSC that is calculated, so in megapascal, and this RMSC is calculated for the different models as a function of the maximum degree used in this model. So what we can see here is that if you take the degree 1 here, we get a pretty high RMSC, which we can see here on this plot, because as you can see here, when you look at the degree 1, it makes a lot of error. So there is a big distance, there is a big Euclidean distance between the model, the yellow line or the orange line, and with the data that you are using. There is a big difference between your model and the data, so you will get a big MSC and a big RMSC. When you increase the degree, so you move to degree 2, the error becomes much lower, so your model is becoming much better. Degree 3, you get an even lower error. So in the case of degree 3, you can see this error here now becomes much smaller, like the distance between the data points that you are using and the model that you are fitting to those data becomes much smaller. But as you can see here, if you move to degree 4, degree 6, etc., the errors still continue to decrease. And if you look at this model here for degree 10, there is really a very, very small error that your model is making. Like it's really going through every single point of the data set. So the Rms C becomes very, very low as you increase the degree, as you increase the complexity. So just looking at the error does not really allow you to distinguish what would be the best model in this case. That's not the right method to look at what is the best degree to take in this case. So here, if you try to fit your data with just a degree 1 model, clearly this model is too simple. So when you have something like this, we will call this types of model underfitted. The reason that we say that is because the model here does not have enough complexity, so it does not fit properly all the complexity of the model, so it's underfitted. It doesn't have enough degrees of freedom. You cannot fit those data properly with by having only 1 degree of freedom, by having only 1 linear term. So in this case, this type of model, we also can, sometimes they are called model that have a high biased model. Why? Because those models think that reality is very simple. This model think that there is just a direct linear relationship between the strength of concrete and the water to cement ratio. So it's biased in the sense that it thinks reality is much more simple than what it actually is. So in that sense, it is biased because it underestimate the complexity of the real relationship between the input and the outputs. So in this is what you would get with a model that is too simple, and that's something that we want to avoid, because this type of model will never give you something completely crazy, but it's nevertheless not gonna give you some very robust prediction. For example, here in this case, if you are using this model that you just developed to predict what would be the strength of a given concrete for a water to cement ratio close to 0.1, the model would predict a very high strength, but in real life, the concrete actually would have a very low strength, or much lower strength than the prediction of this model. Because in this case, the real nature of the concrete is that if you don't put enough water in the concrete, then at some point, like, you won't get enough strength. Like, if you don't put any water in the concrete, then it's not going to gain any strength at all. So your model would just ignore this fact, and it would think that the strength keeps increasing as we put less and less water, and it would think that even for 0 water the strength would become very high, which is not the case in real life. So this types of model is biased because it underestimates the complexity of the relationship between the amount of water in concrete and the strength of concrete. And then on the other side, so you have the case of a problem that is too complex, a model that is too complex. In this case, we will call these types of model overfitted, which is kind of the opposite as underfitted. In this case, the problem with this, in this case, it's a degree 10 fit. The problem with this is that the model starts to fit the noise of the data. Like, the model is so complex, it has so much degrees of freedom that it can really start to go through every single point, and it starts to fit, to be deformed so as to fit the noise of the data. So for example, if you had like a simple linear model like this, and if you were to measure some points, you will never get the true value. Every time you make a measurement, you are going to make some errors. And if you train a model, if the model is going to go through every single point, now you have a model that is fitting not the data themselves, but the noise of the data. And that's a problem that we want to avoid, because as you can see here, again, if you have a model like this, a model that keeps the memory of the noise of the data rather than keeping the memory of the true function behind the data, these types of model will also give you some pretty unrealistic predictions. For example, if you look at here, you try to predict what would be the strength of a concrete with a 0.25 water cement ratio of 0.25, it would give a very low strength, which is not very realistic. If you look at what would be the strength here, it would predict something very high, which again is not very realistic. So this types of model that is too complex, that is overfitted, is also not going to give you realistic prediction. So it's not going to be useful in practice. It's going to look very good because it fit the training data very well, but in practice it won't make any realistic prediction. In this case, so this model doesn't have a high bias, like it assumes that the relationship between input and output is very complex, so there is no high bias, but this model has a high variance in this case. In this case, this model will start to fluctuate a lot. So typically we refer to those models as being high variance model. So you have the high bias model, which is something that we want to avoid because those models are too simple. And then we have the high variance model, which again, we want to avoid because those models are too complex. In both cases, when you have a model that is either too simple or too complex, this is going to be harmful for the ability of the model to make realistic prediction. In both cases, those models would be unrealistic and would not give realistic prediction for the strength of new unknown concretes. So a good way to estimate the accuracy of the model and the reliability of the model would be to assess, can they predict future data? If in the future you add some new measurement of new concrete, so if you add some extra points where you add new points of concrete that are measured and that you add in your data set, if you have a model that is too complex, it's going to make a terrible job at predicting those new data that you are adding to the data sets. So it's these types of models that are overfitted. The way we refer to those models is that we say that those models, they do not generalize well. They do not generalize well. It means that those models, they cannot predict future data. The problem is that if we want to test the reliability of the model, we cannot wait to have future data. Like if we had those data already, then we would have incorporated them in the dataset. So we cannot just wait for the future to see if those models were right or wrong. So we will need to find another way to simulate this thing, to simulate the fact of having future data and to test the ability of those models to predict future data. So in practice, the trick that we are going to be using in order to make sure that the model that you are training is not underfitted or not overfitted is that we are going to simulate the fact that we are going to have some future data. So again, if you had some future data, then if you add some new points in the future, then it's very easy to realize if your model was underfitted or overfitted. Like in this case, this model is very likely is very highly overfitted because it has a very low ability to predict future measurements. Some of them will be well predicted, but a lot of them will have a very high error. It's a very high variance model in this case. So since we don't have any future data just yet, what we are going to do is to simulate the fact that we have some future data. And the way we can simulate this is to say that we are going to keep a certain fraction of the data unknown to the model, and we are going to use them later on validate the model. So in practice is that, for example, here we have a given number of data points that we use to train the model. So in this case, we have about 20 data points that we have used so far to train the model. So far we used all those 20 data points. But if we want to have the ability to test the reliability of those models, then what we need to do is to keep a certain fraction of those data points and to keep them unknown to the model, and to use those points at the end to test the model. So what we are going to say is, if we start with those 20 points that we have, what we are going to say is that actually we are going to use only a given fraction of those data points. Maybe we are going to use only 15 points to train the model. So we're going to keep 5 points away. We are going to pretend that those 5 points are not there. We are going to train the model based on only 15 points, and we are going to keep 5 points, and we are going to keep those 5 data points until the very end. So those 15 points, we are going to train the model based on those 15 points. So those 15 points, this is what we are going to call the training set. And then we are going to keep those 5 points at the end, and we are going to pretend that those 5 points are future data, and we are going to see how well the model can predict those future data. And those 5 points, in this case, we are going to call it the validation set, because we keep those 5 points to validate if the model is too complex or not enough complex. So it seems a little bit counterintuitive to do that, because in machine learning, the more data you have, the more accurate the model becomes. Like, the model only learns from the data. So it's very easy to think that I should put as much data as possible to the model so that the model can become better. But actually, in practice, we cannot do that. We always need to keep some of the data invisible to the model. We only need to train the model based on a fraction of the data, and we always need to keep some data as a backup to test how well the model is doing. It's very important to do that, even though it looks counterintuitive to not use those data to train the model. Like, you would think that you would just use the entire sets of data, because the more data I use, the more the model can learn the relationship between the input and the output. But in practice, it's very important to always keep a fraction of the data hidden to the model, because otherwise you have no way to know if the model is overfitted or underfitted, or if it's the right complexity. So what we will do in practice is that if you start from your entire training set, so if this is your data sets, so this is the entire collection of data that you have accumulated to develop a machine learning model, what you always need to do in practice is to say that you are going to select a given fraction of those data as a training set. This is the data that you are going to use to train the model. So those are the data that the model is going to learn from to infer the relationship between the input and the output by using linear regression with the gradient descent algorithm, etc. And then you are going to use another fraction of the data as the validation set. And so this validation set can be somewhere between 10 to 30% of the data. That depends on the data set. That depends on the number of data points. Like, there is no clear criterion. Like, you can keep anywhere between 10 to 30%. It really depends on the types of data set that you have. But those 10 to 30% of the data, this validation set, is going to be very important, and you need to train the model only based on the training set. And then at the very end, once the model has been trained, you will test its accuracy based on the validation set, and that's going to tell you if the model has the ability to predict future data or not. So sometimes some models that look very good when you train them based on the training set, like they are very accurate at reproducing the training set, then they will become very bad at predicting the validation set because they are overfitted or underfitted, or most likely they are overfitted in this case. So that's what you want to avoid. So to avoid having an overfitted model, you always need to make sure you keep a fraction of the data as being unknown to the model, and then at the very end you can validate whether your model is overfitted or not. So now this is what it would look like if you use the validation, the splitting into training set and validation sets. So here what we did is, rather than training the model based on all the 20 data points, we split the model. We do a splitting of the model into a given fraction that is used to train the model, so the training set, and we split this with a validation set. So we split the data set into a training set plus a validation set, and we train the model only based on the training set, and we validate how well the model generalizes by comparing its prediction to the validation set. So typically the way you can do this is by splitting randomly the data that you have. So you start with all your feature and all your observations. So you start with all the data points that you have, and randomly you are going to pick, let's say, 70% of the data. Those are the ones that you are going to use for the training. So those are going to be the one that you are going to use for the training set, and you are going to pick the remaining 30% randomly that you are going to use to validate the model. And the main idea here is that you still know those data, like you know exactly about those data that are in the validation set. You know exactly what is the value of the observation y. So you are going to use this as a test for the model. You are going to use to see how well the model can predict this value. So based on this, you are going to train the model based on the training set. Then the first thing that you can do is to look at how well it can predict this training set. So usually it's not very hard for the model to properly predict the training set, because that's what you use to train the model. So if the model is complex enough, it's going to be able to properly reproduce this training set. So what you are going to do to at least make sure it's complex enough to properly reproduce this training set is to calculate the Rms C, so the error that the model is making when compared to the training set. So you're going to calculate first you're going to calculate the MSC by summing now only over the point of the training set. You're going to compare the prediction of the model with the true value that you are using to train this model, but you are going to do this sum only on the value of the training set. You are going to divide by the number of points in the training set and take the square root of this. This is going to give you the error of the model in interpolating the training set. So this is going to tell you how well the model can interpolate the training set. And then you are going to now calculate the same thing, calculate the Rms C of the validation set by looking at how well can your model generalize, how well can the model predict those data points of the validation set. So it's going to be exactly the same thing. Now you are going to take the difference between the prediction of the model over the validation point. You are going to look at, for the points of the validation set, you are going to, those are points that were not used to train the model, but nevertheless you are going to look at what is the model predicting, at those points. You are going to compare it with the real observation value in the validation set. Take the square, take the sum of all those values, divide by the number of values in the validation set, and then take the square root to get the Rms C. And this score is going to tell you how well the model managed to generalize. So you have the Rms C for the validation set. It tells you how well it can interpolate the point that it is trained on. So how well can it interpolate the training set. And this score here, the Rms C of the validation set, tells you how well does it generalize to new unknown data that were not included during the training. And ideally, a good model should have a low Rms C, a low error for the training set, and also a low error for the validation set, a low Rms C for the validation set. So now if you look at what you get for a degree 1 model, so here the data have been split already. So the data that are represented at crosses like this is the training set, and the data that are represented as a circle like this is the validation set. Those are the points that are not used to train the model. The model has never seen those data points. They were not used to train the model by the conjugate gradient, but we are just using it now at the end to test how well the model is doing. So here it's a degree 1 model, so it's too simple anyway. So it does a bad job at interpolating the model. If you look at the error for the training set, it's making a pretty big error. I mean, it's not terrible, but there is a pretty big error. It does not properly interpolate the training set. So if you look at the Rms C for the training set for this model, you find an Rms C of 6.2 megapascal, which means that in this case it predicts roughly with an accuracy of 6.2 megapascal, which is not good enough, not satisfactory. It's not crazy, but we can do better than that. But like if you look now at the accuracy of the validation set, then it's even worse. Like if you look at the error that the model is making for the validation set, then it's making some pretty big error. So the Rms C for the validation that we get in this case for this model is 10.9 megapascal. So it's not very successful at predicting the strength of new concrete that it has never seen before. So now let's take the case of a degree 6 model. So now if we look at how well does the model manage to interpolate the training set, then it's pretty good. Like if you look at the training set, it looks like it's doing a pretty good job at interpolating the training set. The error is pretty low. And indeed, if you look at the Rms C of this model for the training set, the error that you find for this degree 6 is only 2.2 megapascal. So it's really having a low error in predicting the training set. It's very accurately interpolating the training set. But the main problem with this model, which is obviously overfitted, is that now when you're trying to predict the validation set, then now you are making a big error. Like the model does not generalize well. And when you look at in this case the Rms C of the validation set for this model, the Rms C of the validation set is very high. You find it's 38.8 megapascal. So it's a very big error. It's making a very big error. It predicts some crazy thing for the validation set. So this model is clearly overfitted. So here you have a case for degree 1, you have the case of a model that is underfitted because it's not properly interpolating the training set. So when you have a model that is making at the same time a big error for the training set and a big error for the validation set, then it's most likely a model that is underfitted. So this one is underfitted. It does not properly interpolate the training set, and in this case it's a model that is likely overfitted because it's doing an excellent job at predicting the training set, at interpolating the training set. The error for the training set is very low, but in turn it doesn't generalize well at all. The error for the validation set is very high. So this is the signature of an overfitted model. So, and then you have the case of a degree 3. So if we first look at the training set, so it's doing an okay job. It's not as good as the degree 6, but it's still properly interpolating the training set. So if we look at the Rms C for the training set, in the case of this model for a degree 2, what we find is that its Rms C for the training set is 3.5 megapascal, which is not as good as the Rms C that you get for a degree 6, but it's still better than the one that you get for a degree 1. So in this case, you have the case of a model that makes a decent job at interpolating the training set that it is trained on. But the real test is to look at the ability of the model to generalize, to predict the validation set. So if we look at the validation set, again, it's not perfect, but it's doing a fairly decent job at predicting the validation set. So when you look at, for this model, the Rms C for the validation set, what you find is that the Rms C for the validation set is about 4.0 megapascal for this model. So in this case, it's predicting almost with the same accuracy the training set and the validation set, which is typically the signature of a good model. A good model should predict with the same level of accuracy the points that it is trained on and the points that it is validated on. It means that this model is predicting as well the point that it is trained on, the training set, and in the future, when you will provide some new points, or you will try to make some new prediction for future points, it's going to give you almost the same accuracy. And when you have a model that can predict with the same accuracy the training set and the validation set, and if this accuracy is low enough, if it can properly interpolate the training set, then that's the signature of a model that is likely a model with an optimal degree of complexity, that is not overfitted and not underfitted. So a quick way to find the best level of complexity for a model, like to find, like, for example, between a degree 1, a degree 6, or a degree 3, like the best way to quickly see which types of model is too simple. So a model that would be, in this case, underfitted, a model that would be biased, a model that underestimate the degree of complexity of the relationship between input and output, and how to also identify a model that would be too complex, a model that is overfitted, a model that has a high variance, in this case, a model that would predict some high fluctuation like this, a high variance model. So you have the high bias here, which is not good, and then you have the high variance, which is also not good. One quick way that you can do is to plot the MSC as a function of the degree of complexity. So in this case, the degree of complexity of the model is just the polynomial degree, the maximum polynomial degree that you are using in the model. So in this case, I'm plotting on the same plot the Rms C. This one is the Rms C for the training set. And this one is the Rms C in yellow of the validation set. And when you are plotting those two Rms C on the same plot, then it becomes very easy to look at the case of the model that are overfitted and the case of the model that are underfitted. When you have a model like this that is predicting a pretty high Rms C even for the training set, like here we have a training set error that is pretty large, then this is a signature of an underfitted model that does not manage to properly interpolate the training set. And then when you see something like this, when you have a big gap between the validation set and the training set, then you have a model that does not generalize well. This is the signature of an overfitted model. In the case of an overfitted model, the training set is very well interpolated. The error is very low for the training set, but the error becomes very high for the validation set. In the case of an underfitted model, the error will be high both for the validation set and for the training set, because the model not only doesn't generalize well, but also doesn't succeed at properly interpolating the training set. And then the criterion that you can use to determine what's the optimal degree, which in this case would be a degree 3, is to see for which degree the model is the best at generalizing, for which degree is the model the best at predicting future value. So in this case, this degree 3 offers an optimal degree of complexity. It allows the model to be complex enough to be properly interpolating the training set. This is what you can see here, because the Rms C of the training set is pretty low, but it's also a model that can predict the future pretty well. It's a model that generalizes well. So in this case, the Rms C of the validation set, which plays the role of future data, is also pretty low. So that's the case of a model that in this case is the best balance between overfitted and underfitted. So it has the right level of complexity that allows you to have a model that is going to be reliable and that's going to make some realistic prediction for future concrete. So there is one last thing that we need to talk about, which is the role of how do you choose the validation set. So far, what we said is that you would start with your entire data set, like the total number of points that you have, and that you would break it down. You would split it. You would do a split between the training sets. You would take, let's say, for example, 80% of the data that you would use for training, and that you would use the remaining 20% to validate, to test the ability of the model to generalize and to optimize the degree of complexity of the model. So this is what you would have if you just use a fixed validation set. The problem with this approach is that it's going to be better, clearly, than using the entire data set as a training set, because now you are holding off on some data that you use to train the model. But there's still something not satisfying with this, is that maybe you could have gotten different result by using some other 20%. Like if you have decided to pick some other data points than those 20%, like if you actually decided to pick another 20% of the training set, then maybe you could have gotten some different results. So if you have a very large data set, when you pick randomly 20% of this data set, then usually you can be confident that this validation set is not going to be biased. It's going to be a good representation of the entire training set, of the entire data set. But if you have a small data set, then if you don't have so many points, then when you pick randomly 20%, then you have a pretty high chance that your validation set might not be fully representative of the data set, and that in this case the Rms C that you will get for the validation set might depend on what is the choice that you are making. Like when you pick randomly this validation set, if you pick 2 times and you randomly 2 times pick a validation set, you will pick different points every time you restart, and you will get potentially a different result at the end. So one way to avoid this degree of arbitrariness of how you select your validation set and the fact that you might get different results based on different repetition with different validation set is to use what we called k-fold cross-validation. So k-fold cross-validation is a technique that allows you to validate the ability of a given model to generalize, to optimize the degree of complexity of a model, but without having the arbitrariness of selecting a fixed validation set, which potentially might not be representative of the entire data set. So the way cross-validation works is it's pretty simple, is that you are going to start with your entire range of data, and you are going to split it into k folds, where k is an integer. So for example, if you are using 5-fold cross-validation, then you are going to split randomly your data set into 5 folds. So you are going to split it like this. 1, 2, 3, 4, 5. Okay, so that's 5 folds. You select them. You split it into 5 folds, where each of them is going to be made of 20% of the data sets. And then what you will do is exactly the same as what you do when you have a training set and a validation set. What you will do first is that you are going, as a step 1, to select the 4 first fold, and this is what is going to be your training set, and you are going to use the remaining fold as a validation set. So far it's exactly the same as what we did in the case of a fixed validation set. You are going to just use the 4 first fold as your training set. So in this case, this is still 80% of the data, and you are going to validate your model based on the remaining 20%. So based on this, you will calculate an Rms C for the training set, just like you would do in the case of the fixed validation set, and you will calculate an Rms C for the validation set in the very same way that you would do in the case of a fixed validation set. But then the difference here is that now you are going to restart. You are going to, as a step 2, now you are going to select a different validation set. You are going to say, now I'm going to choose this fold as my validation, and I'm going to use the 4 remaining folds as my training. So you are going to now train the model based on still 80% of the data, but on a different 80%, and you are going to validate your model based on a different 20%. And again, you're going to calculate the Rms C that you get for the training set and the Rms C that you get for the validation set. And then you will repeat that k times, where k is the number of folds. So in this case, you will repeat that 5 times, where you will select now, in step number 3, you will select this fold. Step number 4, you will select this fold. step number 5, you will select this fold as your validation set, and you will always train the model based on 80%. That's going to be your training set. So you always train the model based on 80% of the data, and you validate it based on the remaining 20%. And so what you will do is that you will do that 5 times. Since you have 5 folds, you have 5 different folds that you can use as a validation set. So you can train your model 5 times, and each of those 5 times you will calculate the Rms C of the training set and the Rms C of the validation set. And then what you will do is that you will just take the average of the Rms C of the training set over those 5 repetitions, and you will take the average of the Rms C of the validation set over those 5 repetitions. And that way it will give you a more average response of your model. It will tell you a more average representation of its ability to predict the strength, the concrete strength for unknown concrete, because this time you have sampled the entire data set by cutting and by splitting these data sets into 5-fold like this. Now the result that you will get will not depend on how you splitted the data sets into training set and validation set, because you have done it in 5 different ways. So you will get a more average response of your model. So it's a more robust way. It's more computationally expensive, because now you have to train your model 5 times instead of just once, but now you get a more average response. So it's a more accurate way to determine if your model is going to be underfitted or overfitted without having an arbitrary choice of the choice of the validation set. So what we will do now, so you know already quite a bit of theoretical information on how to train a model, how to make sure that this model is not underfitted or not overfitted. So in the next lecture, what we will see is how to do it in practice by, in this case, by using MATLAB, how to implement those ideas that we just saw, to how to do it in practice in MATLAB with some arbitrary data. What are the commands to use on how to train this, how to split the data into training set and validation set, how to optimize the model by gradient descent, how to calculate the Rms C, and how to determine the best model that you can later on use to make some predictions. So the next lecture will be more like a tutorial on how to implement those things in MATLAB.